Hi, Assalamualaikum. My name is Muhammad Daniel bin Muhammad Shah, and my teammate is Dr. Najidah Hamadi and Dr. Nurul Nadia Muhammad. We are from Faculty of Electrical Engineering from University Technology Mara UiTM Shah Alam, Selangor, Malaysia. Our project title is Nonlinear Modeling for Time Varying Water Temperature PID Control. So for introduction, system identification is a method of using system input and output data to create a system mathematical model that is commonly used in various fields of production and life. The system identification contains a linear and nonlinear modeling. Nonlinear models can present much better approximation than linear models since it can capable of characterize systemic behavior over the entire operational spectrum relative contrasted linear models that estimate the structure across a specific operating point. Then distillation column system is one of the common methods use linear and nonlinear modeling equally, such as autoregressive with exogenous input ARX and nonlinear autoregressive with exogenous input NARX. There are several controllers have been implemented for the distillation column, such as dynamic metric control (DMC), predictive functional control (PFC), globally linearizing control (GLC), and model predictive control (MPC). For the problem statement, distillation column has been presented a tough effort and have become critical issue because of its primary nonlinearity of distillation, multivariable dealing, the non-stationary behavior, and the hardness of disruption. Then, difficulties analysis involve restriction in describing physical process, dominant nonlinear, and time-varying behavior under transient condition of the process, such as startup method and set point changes, time-varying several adaptations, connection and nonlinear problems. Then, PRBS input signal might not suggest suitable data to identify nonlinear behavior since it consists only of two levels. Consequently, the signal cannot excite certain nonlinearities. After that, there is some limitation demonstrated in nonlinear modeling system by using linear method due to the validity of specific input range. To date, only a limited number of perturbation input signal investigation on the observed distillation column have been identified. Currently, only a limited number of PID control for distillation column using nonlinear modeling have been identified. The objective of this research are: number one, to construct a NAREX model of the time-varying water temperature through steam distillation pilot plant (SDPP). Number two, to estimate a transfer function based on the nonlinear model. The third one, to evaluate and compare the performance using Ziegler-Nichols and Cohen-Kuhn control technique of proportional integral derivative PID. So for the methodology, on the left side is the picture of the setup of steam distillation pilot plant. SDPP was used to obtain the temperature data. The distillation column with 12-liter water is heated by immersion heater. It produces steam that will pass through plant material for essential oil preservation. An excellent plant response prediction is important in preparing the nonlinear modeling from the real-time plant. Besides, the sustainability of the process, quality and quantity also depends on the temperature. It's one of the critical parameters that is considered in this project. For temperature, there are two input perturbation. There are two input perturbation input signal that were used, such as PRBS and multisign. When the temperature data from SDPP was produced, MATLAB software and system identification app were used to obtain model output. The number of poles and zero were set in system identification to obtain the best result of the transfer function, and all model output were estimated by using the parameter estimation. The model output of each transfer function was then evaluated, and the transfer function is selected by its best fit, final prediction error, FPE, and mean square error, MSE. So as you can see on the right side, there are 4 pictures indicating the system identification app. The first picture is model output for transfer function. The second picture is model estimation. Then the third picture is simulated model output, and the last one is model validation. From the temperature output response, an open loop test and process reaction curve were conducted to find first order plus that time FOPDT model. The value that we need to gather is number 1 gate, number 2 temperature at 28%, number 3 temperature at 63%, number 4 time constant, and the last one is time delay. To find gain, gain is equal to output divided by the input. Output is equal to the highest temperature minus with lower temperature, while the input is equal to highest value of input minus with the lowest value of input. After we find the value of temperature at 28% and 63%, we need to locate it based on the temperature output response to find the value of X at 28% and 63% respectively. Then we will follow the next formula, which is time constant and time delay, to find the value. When the value of FOPDT had been gathered, we will proceed to the next step, which is to calculate the PID tuning rules. In this project, there are 2 PID tuning rules, which is Ziegler-Nichols and Cohen-Kuhn. For every PID tuning rule, we need to find the value of proportional gain, Kp, integral time constant Ti, and derivative time constant Td. When all this value has been gathered, we will use this value to put inside the Simulink in MATLAB. As you can see on the right side is the example of Simulink PID block diagram. As you can see, there is Kp, Ti, and Td. All the value that we have been gathered will use and will be entered into this block. On the right side, we have transfer function that we obtain from system identification app. Then the next one is result. There are 2 input, which is PRBS and multi-sign. So from this input, we will obtain the value of feed, FPE, and MSE based on the number of input and output term. For every input and output term, we use 4 number, and from there we compare which one give the best value. For the experiment, we use 3 band for M-sign and PRBS, which is 0.1, 0.5, and 0.8. The next one. This is the PRBS input model. So for the output from PRBS band, the value of TR and TS in the Ziegler-Nickel PID tuning produce faster response compared to Cohen-Kuhn for band 0.5 and 0.8, but slower response for band 0.1. However, Cohen-Kuhn demonstrated lower value of percent overshoot compared to Ziegler-Nickel for band 0.1 and 0.5, but higher for 0.8. Then the comparison of ISE shows Ziegler-Nickel PID tuning produce lower ISE, better than Cohen-Kuhn for all band. The next one is for multi-sign input model. For band 0.1 and 0.8, Cohen-Kuhn recorded lower time rise, settling time, percent overshoot, and ISE, integral square error, compared to Ziegler-Nichols. For band 0.5, Cohen-Kuhn demonstrated lower rise time, percent overshoot, and ISE, while Ziegler-Nichols produced faster in settling time. In conclusion, NAREX model PID control was used for performance in investigation based on several tuning rules. The result proved that the Ziegler-Nichols tuning method demonstrated better performance compared to Cohen-Kuhn for PRBS input values, while Cohen-Kuhn tuning method revealed as better performance compared to Ziegler-Nichols for multi-sign inputs. That's all from me. Thank you very much.